All right, let me introduce you, Vitaly. And so this is the classic panel of our Scale by the Bay conference. Welcome everybody who is joining us for the panel. We have the history of really interesting debate panels, and Vitaly was the one who actually introduced this format. We had several debates in previous years, including, what will happen if everybody will move to the cloud, and functional programming for machine learning, whether that will take hold. And I think actually it does, and I think we are moving to the cloud. So today the topic is hardware versus software in various aspects. I think AI is a big theme, but also there are many others. Again, Vitaly is our fearless moderator. So I'll introduce Vitaly. Vitaly basically built Salesforce Einstein, which is a combination of software engineering and data science. And so this is the way we like it, really, because it's basically scalable first application of AI, where focus is on high quality engineering, strongly typed programming, Spark, which we love, right, and kind of multi-tenancy and so forth. And now Vitaly is the CEO and founder of Faros AI. Vitaly will moderate this panel. He set the rules, and I believe he will let the panelists introduce themselves. So Vitaly, take it away.
Hi, Alexei. Thank you for the nice introduction. So folks, for those of you who've never seen this kind of format before, we're going to do kind of a friendly panel, friendly debate between two teams of two arguing kind of a motion, and then we'll see which kind of one of you were moved the most from kind of one side to another by kind of the arguments that were made. The history for this panel, this debate started at our previous debate where there was a comment made about hardware versus software, and we decided that we should continue this conversation a year later. So as you folks know, all the increased cloud computing, on one hand, it seems that kind of hardware is being abstracted by compute APIs. On the other hand, there is a resurgence in a lot of amazing companies and development in Silicon, and there is definitely now a sense where something that was thought about previously as a commodity becoming is actually a very interesting play where people are taking notice. So that sounds like a making of an interesting debate. And like I mentioned, we have two teams of two argue for and against motion that hardware or compute is like electricity. People will not care how you get it. And arguing for the motion, meaning that hardware will be abstracted, are Alex O'Connor and David Canter. Maybe David, you can start by introducing yourself.
Absolutely. So I am one of the founders and the executive director of MLCommons. For those who are not familiar, it is an open engineering organization that focuses on making machine learning better for everyone. We do the industry standard MLPerf benchmarks, which I had the privilege of leading the inference ones. We also build large open data sets, and I'm thrilled that we have two of them that are going to be released at NeurIPS this year. And then we also work on best practices to sort of eliminate the frictions that you have in using machine learning today. And perhaps particularly relevant to this, I have a long history in sort of semiconductors, microprocessor design, other hardware related things. So naturally, I was stuck on team software.
Yep, we like to keep it interesting. So, and your partner is Alex. Alex, can you please introduce yourself?
Hi, everyone. I'm a senior manager for data science and machine learning at Autodesk. In particular, I work on our e-commerce and customer empowerment team. So we work in personalization, natural language processing, and the like, and we run our support and assistance chatbot, Ava, which is firmly on the side of software as well. So I'm looking forward to the opportunity to debate.
Awesome. And the side arguing against that is that actually hardware will have its resurgent moments and will become more and more important are Anna Goldie and Bryan Cantrill. Anna, perhaps you can go with introducing yourself.
Hi, I'm Anna Goldie. I'm a staff research scientist at Google Brain, and I'm a co-founder and co-lead of the Machine Learning for Systems team there, where we focus on machine learning approaches to various problems in systems optimization and chip design. And recently we published a paper on reinforcement learning approach to chip floor planning that I'll talk about later today.
Awesome. And also Anna, did not mention that she was also kind of recognized this year as one of the 35 innovators under 35 by the MIT Technology Review. And Bryan, you were not recognized as one of the 35 innovators under 35. So what do you have to say for yourself?
Vitaly, I actually was. I was in the TR35 in 2006. So
probably for D-Trace, right?
I'm saying this year, Bryan.
This year it's tough. You know, unfortunately they've got a TR35. They don't have a TR47, unfortunately. So I'm considered to be out to pasture. So I'm Bryan Cantrill. I'm the co-founder and CTO of Oxide Computer Company. I'm very happy to join Anna on the pro hardware side of this fierce debate. And to watch David get uncomfortable arguing a position that he doesn't necessarily believe in. We are Oxide at Oxide. We are building a rack scale machine, bringing the innovations from the hyperscalers to the mainstream enterprise on-prem market, with the big thesis that Jeff Bezos is not going to own and operate every computer on the planet. So excited to be here.
Oh, wow. We already at kind of I think the 21st century Goodwin law already of how long does it take to mention Jeff Bezos? So we'll do it in kind of a panel of interviewing. So there will be a first step where basically every side will introduce kind of their opening statement, about 5 minutes per person. Then we'll have some questions from the audience and from me, and eventually we'll have some closing arguments, and we'll hopefully some friendly debates in between. So the side arguing kind of for David or Alex, who wants to go first?
Alex, yeah, let me start.
Go ahead, David.
All right, so I believe I've got 5 minutes, so I'll trust you to keep me honest on timeline.
Yep.
I want to point out, so I actually studied math and economics at the University of Chicago. Unlike everyone else here, I actually don't have a background in CS except for a minor. So I'm going to actually take a tact from my economics training. And so I claim that actually AI is not too dissimilar from a wide variety of other technologies that are frankly, to our ancestors, magical. Things like electricity, flight, automobiles, right? And or real-time ad bidding, for instance. And so, if you look at all of these things, the way it evolves, you can look at the history of flight. Like we started out, and there were people designing planes that were like a bicycle with wings that would flap its wings like a sparrow. And, as it turns out, that actually doesn't work. And so the aero, like the Dreamliner works on a slightly different set of principles, as does the 737 MAX, right? And so, what happens is you have a natural maturation where the way a lot of these technologies work is initially they are, very raw and exposed. There's all sorts of things that matter. What plane are you on? The safety ratings are very different. The ranges are very different. But as time goes by, you ultimately get the beauty of software actually is sort of forced by economics, which is you have layers of abstraction, right? And that happens due to the economic system. And, it happens in software as well because it's a good engineering practice. But if you look at electricity today, right, most people, probably 90%, don't actually really think about where their electricity comes from, right? Now, if you're in California, it's in PG&E. And, we're really only reminded of where it comes from when things catch on fire in Napa Valley. But, realistically, that layer of complexity, generation, distribution, inspecting right-of-ways, that's all hidden, right? And so if we look out 10, 15, 20 years, if we want AI and ML to really be profoundly shaping our world, that's where we need to head, right? So the mechanism for that is, again, layers of abstraction. And so, if you want to look at take some of the most remarkable capabilities out there, say Google's T5 model, which is my understanding bigger and better than GPT-3, but GPT-3 will work, right? Macy's and Goodyear will never train GPT-3, right? We are going to have a small number of companies with that capability that focus on it, that have the systems understanding to tackle that problem. And then the rest of the world will kind of collect that bounty downstream, right? And so, if you were to look at it today, you might say it's going to be transfer learning or fine tuning or delivered via an API, right? Where, maybe, you just send to the cloud, your image, and then it comes back and says, okay, UPS just dropped off a package, go grab it before, your neighbor does or whatever, right? And so that's sort of where I anticipate that AI and machine learning will ultimately evolve, which is the complexity around hardware and low-level things like math kernels and like what are your hyperparameters for training. All of that needs to get hidden. Same thing for the entire deployment pipeline, right? Even if you have a trained model like what Anna and her team produced for RL for chip design, ultimately getting that deployed is a very non-trivial endeavor. And so removing that friction is actually what's going to unlock a lot of AI capabilities, everywhere. And again, a lot of that is, okay, we need to take this model, we need to get it to, run in the right place. We need to check and make sure it's not going to do something crazy like, accidentally identify that I'm a criminal and send me to jail. Not that a chip design algorithm would do that, but you've got a lot of standard processes that need to be resolved, and all that's orthogonal to hardware, right? This is fundamentally a software problem. And then I think the last point I'd make is I'm a big believer in what I call data-centric AI, right? Which is that ultimately the way we drive up the capabilities of AI is with bigger, more diverse data sets. And again, this is something that is orthogonal to the underlying plumbing, right? If you want to have a self-driving car, the key is getting data on a car operating in winter, right? Which you cannot collect in San Francisco because we just don't get snow, right? So you need to get your data in New York City. And again, that's not really about hardware for AI, except insofar as there might be sensors involved there. So, when I look at the fundamental challenges to really making AI go from like magic that no one understands to magic that operates in the background and everyone takes for granted, which is ultimately what we want, it's about software. So I rest my piece.
And thank you, David, right on time. So Bryan or Anna, who wants to go first for this side arguing against?
Go for it, Anna.
Okay, I can start off. So I guess it's always great if you can abstract away the hardware, but I think the problem here is that, all this progress that we've been making in AI and machine learning has been fueled by advances in hardware, and the effective compute that we get from hardware is a function of like the fit between the algorithm that's running on that hardware, right? And so therefore, we unfortunately cannot ignore the hardware that we're running on. Like we've been running various like experiments on, how can we do hardware software co-design? And it's clear that you can get multiplier improvements in performance if you do a better job of this like co-optimization task. And so I think that the future very much like requires that we focus on the properties of the hardware and the software together. Maybe Bryan, do you want to add to that?
Sure. Yeah, I totally agree. And we're definitely team hardware software co-design here. My view is if you look back at the last 40 years in hardware and software, hardware has been Moore's law has dictated the direction that hardware has and has dictated the revolution in hardware. And I think the most important revolution in software has been open source. Which sounds trite to say, but the older I get, the more I appreciate how important open source software is. It's been interesting for me to go back and read. Of course, I lived through this, so I should remember this, but reading tales of software development in the 90s feels foreign to the modern software engineer, because so much of the trials and tribulations of software development in the 90s was due to proprietary everything. Compilers were proprietary, operating systems were proprietary, databases were proprietary. You couldn't do anything without consuming proprietary software. The open source revolution has been extremely important for software. Moore's law has been extremely important for hardware. We are on the cusp of those now flipping. I believe that open source is going to become extremely important for hardware. And I believe that the end of Moore's law is going to be extremely important for software. So Both of these mean that the other is going to have to learn from these previous revolutions. I mean, if you look at, to take the open source revolution to hardware, we talked a lot in the 80s and 90s, early 2000s about reconfigurable computing, and people kind of forgot about that. Reconfigurable computing is actually really important. The problem is those tool chains have been entirely proprietary. Anna's exactly right about the ability to unlock these order of magnitude gains when you design hardware and software together. But in a world of proprietary Xilinx or proprietary Altera or formerly proprietary Lattice, and trying to actually do this, I mean, I feel like I'm going back in time looking at this proprietary software that is expensive, that it doesn't work. It doesn't actually allow us to deliver the benefit of that. I feel like one of our most unsung heroes in computer engineering is Claire Wolfe, and the work that she did to reverse engineer the Lattice bitstream format and allow Yosis to actually allow open source tools to generate a bitstream for an FPGA. This is a total breakthrough that people don't really appreciate. We are now seeing this, I think another breakthrough that people don't appreciate, open sourcing of BlueSpec, a really interesting hardware description language. It's a small demographic, but I think an important one. BlueSpec doing for HDL is what Rust did for software development. And then at the same time, the end of Moore's Law, I agree with a lot of what David is saying about the need to get more and more data. But the end of Moore's Law means that we are actually going to need to focus on the efficiency of our compute. And I think, look no further than the M1 and the interesting hardware software co-design that Apple has done there to achieve great performance, but great performance per watt. That is a real breakthrough there, and we have not yet seen that in the data center. I believe that that's coming. All of that is coming with hardware software co-design.
Awesome. Well, thank you, Anna and Bryan. And Alex, when did you wrap this thing for us?
Sure. Thank you. So I think it's great to see such insightful debate already. I mean, we're shortly into this, and it really does make sense to me to think about, though, what actually the impact of this is at the end of the day, because both Anna and Bryan have done a wonderful job of explaining why at the margins of performance and scale, there are these useful ways to think about how we can fine-tune these things. And to me, that all reflects on what David said earlier about this idea of electricity generation. I'm sure it's super fascinating to get into the experience of, the blade design for turbines. And it's really important for us to think about those sorts of aspects. But ultimately, the real impact of machine learning is not about the choice of specific hardware or the choice of specific stack. It's about this understanding that it's really, it is a flow of data and a flow of automated decision making and speeding up of business processes that actually is the impact of machine learning. And hardware is extremely far from that experience for most companies and most practitioners, and getting further and further away because of the power of open source and because of the power of the commoditization of ML, the pervasiveness of ML features throughout the environment. So to me, I think this is the point. The optimizations of how it works at the end of it, the impact of that is getting more and more distant from day-to-day practitioners and more distant from the experience that people have. We're all using this kind of metaphors in the same way, but what we really need to think about is the fact that the biggest challenge for AI is really not in as I say, those marginal performance gains. It's really about that question of which companies can leverage their data, which companies can transform their business processes, and they will increasingly seek to do that from main providers, from people like from large companies who have the resources to look across scale to perform those experiments themselves, because we're moving from that home inventor that, I wired the thing together myself, put it onto the rack and built it up. This is a cloud journey again, from the 90s where people were kind of installing racks and made out of Lego in their garages. I mean, I hope no one is doing that anymore, right? Instead, we're gonna use cloud provider of choice and GPU of choice, or whatever TPU or XPU of choice from that on. And I think that experience also exists at a now software level, which is people will move away from training their own models or even perhaps fine-tuning their own models, and instead, expose their data to a central provider and, leverage that. And that will be increasingly important because as companies it allows companies to focus their effort. It allows organizations to say, these things that are all the things beside what I want to do as my core competency, I can take best advantage of along the way. And I think that's an essential thing to think about as we think about this experience. The other part of it for me is the disconnection between the place that I train, the place that I develop, and the place that it runs. So, ONNX, all of those sorts of technologies, they are handling it. I'm very happy to allow all of the much smarter people than me in the world to abstract all of that stuff away from me permanently. And I will just be able to say, let's make it go. Let me just, make it go away from me. Let me not have to worry about that in the way that I do today. And if I never have to install an NVIDIA driver on a Docker image again, I will be a happy man. So for me, this is very much the key point about it is that, essentially what we're thinking about here is the real impact of AI is data. The real impact or the real value of that is the fact that open source is about a strategy of coalescing effort and providing many eyes and many hands on the parts that should be shared. And none of those are things that really matter about the hardware so much as they do about the ability to abstract away those concerns in an essential way. And for me, that's what I would think about on this matter. What we're seeing with this is, what we don't really understand, I think, yet, and what we will begin to understand is what this idea of pervasive machine learning is going to do to the developer experience as well. We're beginning to see this idea that, it's moving away from this idea that I think machine learning is a separate role from or is a separate thing that, exists in its own box and is becoming part of every piece of software that you have to develop, and intelligence is embedded that way as well. That's also going to change the tools. That's also going to make it need to be more abstracted away from the hardware, the way all other software is, the way databases are, and the way thread management is, and everything else like that.
Well, thank you, Alex. And again, there were very interesting points made here by each side. And now we're kind of move to kind of a question and answer where, both sides can ask each other.
Hold on. Can I interject? Moore's law is not dead.
Well, you can start with that statement and go for it. So, yeah, why do you think it's not dead?
Oh, okay. So one of my hobbies is semiconductor manufacturing and device physics. And so actually, there was a great keynote from Pat Gelsinger yesterday pointing out that Moore's law is not, in fact, dead. Now, I claim Moore's law is, Brian, you said you would be eligible for TR-47, so perhaps this statement will resonate. But I'm going to suspect you are not in as great shape as you were at 20. And Moore's law is sort of in the same way. At 50, it's just a little bit slower than it was in its vigorous 22, 25-year-old days. When it takes a drink and falls down, it takes longer to get up. But if you look at the innovations that we have coming, you've got things like gate-all-around transistors, you've got stacked CMOS, you've got new materials. I'm actually quite confident that we're going to see a fairly significant improvement in hardware performance. Now, it may not be in the same orders of magnitude that we got historically, but I think we've got another decade to go. And I think, the important thing is that as software folks, you can probably step back and identify that, and from a hardware software co-design perspective, right? If we write all of our code in C and tune it well, we can probably wring out orders of magnitude. But despite that, the most common language for machine learning is Python, which is not performant, to put it mildly, because, the reality is that, and this is what I've always said about hardware design, is when you look at things like caches versus scratch pads, right? A cache is basically an acknowledgement that I want ordinary programmers to be able to get median good performance out of it. And so, I think it's Anna's point, which was that, ultimately there are leaky abstractions and, you can't fully isolate hardware from software is in fact true, right? I would not deny the power of hardware software co-design, but at some point that performance delta drops from orders of magnitude to 10, 20, 30%. And then it becomes a question of, am I willing to drop I see Anna doesn't agree. I can't wait to hear the response. But, I think if you were to talk to any development manager, many of them routinely drop 20, 30, 40% performance on the floor all the time for the sake of getting things out the door quickly, right? I mean, and you can just see that, like, people don't do security, which is a freaking legal liability, because it's like, no, we just need to push out this feature, and please ignore the fact that like everyone's social security number is now a public record, so.
Well, I think let's maybe let Bryan or Anna respond. Feel free to go for it.
And I think you and I are both going to take an opposite approach here. You want to go first, or do you want me to take a swing?
You can take a swing first. I go next.
Yes, we got a real debate on our hands now. The good news, Vitaly, we've got a real debate here. Moore's law is indisputably slowing down. So there's just no question about that. And yes, scoffets are a thing. Yes, we are. I mean, I think citing a Gelsinger keynote as the reason why Moore's law will continue. There's a lot of counterpoints to be had on that. The Intel themselves failed to deliver 10 nanometer in fact, we still don't know what happened with Cannon Lake, right? Cannon Lake was, I've joked that the conflagration at Cannon Lake sounds like a Hardy Boys mystery. But we actually don't actually know why Intel for years failed to deliver. And now we've got a hunch that they failed to deliver because it's actually really hard. We're pushing the physics really, really hard. I feel obligated to say this. I imagine my co-panelists know this, but you in the audience may not realize this, that when we talk about process, we talk about nanometers of the node, of a 7 nanometer node, 5 nanometer node, 3 nanometer node, and so on, 10 nanometers with Cannon Lake. Those nanometers that's a made up number. That is not actually, that's an expression, a rough expression of transistor density. It would be much easier if they talked about millions of transistors per millimeter, per square millimeter, but they don't, or per cubic millimeter. So nothing is actually 3 nanometers in a 3 nanometer process, or 5 nanometers in a 5 nanometer process. The question is, what is Moore's law? Is not an absolute expression of the maximum density achievable by humanity. It's an expression of economics. It is actually cents per transistor, transistors per dollar. That is indisputably ending. It is certainly slowing down. And I'll just make one other point and then hand it off to I'll tag out for Anna to get her licks in. But when we talk about and I think both David and Alex talked about how we're building these abstractions, and yes, it's inefficient, but it's the abstraction that matters. I feel like I'm talking to the auto industry before the 1973 oil shocks about that gas is just infinite. And why would we ever bother to even think about the actual efficiency of our engines? Why would we bother to think about the actual pollution that's coming out the tailpipe? It doesn't matter. It's going to go on forever. It's like, well, and we learned in 1973 and then again in 1979, it actually doesn't go on forever. These are finite things. And when we, at some point, we are going to have to explain to our children and grandchildren how we used our finite fossil fuels and lit them on fire so we could solve math problems and sell them to one another. That's going to be embarrassing. I think that in many regards, this kind of the proof of work that we see in cryptocurrency, it's an embarrassment. It is implying that these resources are infinite. They are not. They are finite. And the way to drive better performance and, importantly, better efficiency, and by better efficiency I mean not unconscionable inefficiency, is going to be with hardware software co-design as Moore's law slows down. Anna?
Yeah, so go ahead. I just want to call out that we already have the topic for our next debate. Cryptocurrency is an embarrassment.
Hold on, is that a debate?
Well, it depends on who we'll find for the other side. But yes, Anna, please go ahead.
Yeah, I mean, I completely agree. Like, whether Moore's law is dead or dying, it's certainly not keeping up pace with the demand that our machine learning algorithms have for additional compute. So if you're looking at some of the data in terms of compute consumption by AI models, it's doubling every 3.4 months. So even back in the day, Moore's law wouldn't be able to keep pace with that. And if you think about like how can we reach our goal with AI? Like if we wanted to get like a 1% error rate on ImageNet, we need many orders of magnitude more effective compute. So like we're just not going to get there without hardware, software, co-design. And in some sense, like additional compute is just a very clear fuel for progress. Like if you see those scaling laws papers by OpenAI, it's just a smooth power law. The more compute we have, the more data we have, the more parameters we have, the better the performance. And it's just we need to do better in terms of our software hardware co-design in order to be able to achieve that. And sure, like maybe Python is like the top language right now for machine learning practitioners and researchers, but really it's just because most of the computation is taking place in these like calls in the TensorFlow or PyTorch APIs to hardware that it happens to run pretty well. Like these matrix multiplies do well on current hardware, but really if you look at say like Sarah Hooker's hardware lottery, there's a lot of machine learning approaches that could be extremely promising. They just don't happen to run well on today's hardware. And if we want to unlock the potential that AI and machine learning has, we need to be able to be more adaptive to these potentially more promising approaches.
Awesome. So, Alex, I want to kind of hand it off to you also kind of to respond, but let me kind of try to up-level the conversation a little bit so we're not kind of dragged on whether, Moore's law is dead, but I want to kind of offer a different perspective. I think Bryan mentioned the M1. So one of the kind of, great jobs I have as a founder of a startup, and Bryan, you probably, share one, and maybe David as well, is that we're also the procurement officers for the laptops for our teams. And as a procurement officer, I have to say that when Apple announced their new M1 laptop, like everyone, came in and like suddenly, something happened to their laptops and they want, they spilled coffee on it accidentally all in the same day. So beyond kind of, everything that is going on is like, there is genuine excitement about kind of those advancements in silicon. So I would also be curious kind of why I think, maybe it's still, doesn't matter. It's all, going to be abstracted anyway.
So I think it's great. I remember someone explaining to me what the extraordinary suicide rate of BlackBerries was the moment any company authorized iPhones back in the day. It was exactly the same thing. Astonishing how all the screens would spontaneously combust at that time. I think M1X is a perfect example, though, of the kind of story that we're kind of the kind of story that we want to make here, which is honestly for most users. I think it's a theoretical, right? Like for them, how many of them will actually connect the fact that there are ML related cores on their hardware to the experience that changes? Not a lot. How many developers? Again, maybe there'll be an advantage there, but ultimately the important point is about how the experience changes and what type of software we're developing and how better integrated it is for the end user and for the developer who's making it. And in my mind, I think that is the ability for companies to do that is where the real interest is in this and the real abstractions. I don't think anyone is arguing realistically that we have the perfect hardware and we never need to move away from that ever again. I mean that's a slightly crazy kind of concept. I don't think it's a realistic one. I think what's important is to ask where is the real value and where is the real innovation that actually is going to be transformative. And I don't think that right now is going to be in the kind of elementary aspects of fine-tuning the hardware. I think that we're at the point now where really we need to move from the laboratory and move into the kind of industrial kind of context level. And that's really where it's about the businesses, it's about the data, and it's about that sort of velocity and all of the ability for us to do the things that the car companies were not able to do around sharing standards and sharing value is actually what we can do. And to me, I think this universal adoption of the abstractions is actually, and the disconnection from the hardware is the freeing of the practitioner and the freeing of the user from concerns that really shouldn't exist.
Yes, folks, this is also kind of to make the kind of Alex and David's point, and Brian and Anna, I would love to hear your thoughts. We are now so many levels of abstraction away in, I would say, let's say the kind of the more common, software development. Even, think about like no code is like a thing that we're talking about. So there is just so much specialty that needs to go all the way, kind of to really start understanding hardware. Like we're now at an age where people don't even know SQL and they're using ORM as like an abstraction layer, right? So kind of Brian Rana, kind of what is maybe the kind of the strongest case that actually besides, and I think maybe David said, or Alex, I think it was Alex, sorry, that there will be definitely on the kind of margins, there will be folks that, care deeply about it, but for the vast majority that actually, they just won't care.
I think another issue that we haven't discussed yet is, climate change, right? With this increasing, this exponential increase in the consumption of compute by various AI algorithms, the carbon footprint is also exponentially increasing. And so depending on the fit between the software and the hardware that it's running on, the power consumption could be radically different. And, it could be that using a certain type of hardware is basically consuming a blood diamond. You are mortgaging the future of our planet, and users cannot be free from the, caring about that if they're a responsible human being.
Yeah, I absolutely agree with that. And Vitaly, I mean, it's a very good question in terms of how do we, I mean, we invent abstraction to allow people to do more work with less lines of code, right? That's what it means to be at a higher level of abstraction. But when you are able to do that, just to Anna's point, you are able to inadvertently consume far more resources than you actually should. And I think for much of my career, I view this as a bit of a paradox about how are we going to resolve this? Because how are we, the software drives us to these towering layers of abstraction, but we know that we lose efficiency. And I mean, I guess this is going to be very on brand for me to say this, but honestly, before Rust, I was becoming a bit dispirited because it felt like the abstraction was only headed in one direction. I think the rise of Rust is really important because it allows people to deliver much higher performing artifacts that are really very, very sophisticated without necessarily needing to have all that sophistication themselves. So, I mean, one of my early experiments with Rust, now coming up on 3 years ago, was wading in with something I'd implemented in C and re-implementing it in Rust. And I was shocked when my Rust outperformed my C. And why is that? Well, it outperformed my C because in Rust, if there is no balanced binary tree in the standard library. In order to use in the standard library, all you have is a B tree. Well, a B tree is actually a much better data structure than a balanced binary tree from a memory locality perspective. And a cache line is now looking a lot more like a page coming off of a disk. And that increase in efficiency is something I didn't have to be aware of that as a programmer. I didn't have to really understand the nuance of that difference. It's the powerful abstractions of Rust that allow me to pull that B tree off the shelf and just use it. And I think one of the great myths about Rust, honestly, is that its rigor gets in the way of the ability to create something quickly. Rust allows you to create things, I think, really quickly, but things that operate with a much higher level of performance and a much greater level of efficiency. So I view that as a really interesting template for the future. I don't think everything's gonna be rewritten in Rust, but I think that it now opens the door to new kinds of languages, new ways of thinking about the problem. Rust shows us that there is a third path where we can allow software engineers to operate at a high layer of abstraction, but deliver a high-performing low-level artifact. And that's pretty interesting.
Awesome. So kind of to wrap things up, and David, I'll kind of maybe give you a little bit more time, but let's kind of finish it and go into kind of the third section. So, please respond to what Brian and Anna said. Also, I would like to just kind of to go off Anna's comment and ask you, David, why are you willing to kill our grandchildren and let them use Python?
That is exactly what I want to respond to. So first of all,
so go for it, and also let's wrap up why people should actually side with your side of the argument.
Yeah. So first of all, I mean, you know, the energy consumption and the impact on climate is a significant one. But I think looking at it in the framework that you have is very much a fixed mindset that precludes potential growth, right? Which is to say, is doing matrix multiplication via PyTorch or TensorFlow really the right way to be doing things? You know, when I look at some of the things that I'm most excited by, it's things like active learning that maybe allow you to cut the amount of data and therefore compute you're doing by orders of magnitude, and essentially to train smarter, to do inference smarter. And so, you know, I am not willing to bet against human ingenuity, right? And if you were to look in the 70s, right, at a lot of these sort of energy related arguments, it's like, oh, we're going to have peak oil or all these other things. The reality is that economics will tend to break a lot of these things. And by break, I don't mean EAK, I mean AKE, right? And so we'll sort of smoothly kind of decelerate on a lot of these. And I think what we'll see is, right, yes, we will be capped in how much power we can consume for compute, and that will drive innovation on many other dimensions, right? But the people who will spend their time fundamentally delivering those innovations, whether they're folks at Google Brain or whatnot, will ultimately make those available from a few number of people to the masses, right? And so I don't think we have a future where it's either we get AI that is magical or we set the planet on fire. I think we can do those both. But again, it requires a huge amount of innovation at the software level, right? Above the level of the hardware, to return to my point. And I certainly hope that's true. I don't want to see San Francisco catching on fire regularly. That would be a serious problem.
Awesome. So
we're going to get magical AI and light the planet on fire. That's right.
No. I'm saying we don't. We.
Yeah. So Bryan, since we kind of started, maybe let's kind of from everything you heard, can you just wrap up and tell the audience why you did such an awesome job and your opponents did a shitty job of explaining their position?
Well, I think that both my my teammate here and I both have seen the power of software hardware co-design. We have seen the inefficiencies that can be addressed, and I can't understate this enough, that the rise of open source is a really critical revolution at this layer of the stack. We have part of the reason we have not seen the gains that we might have otherwise seen, and because we've been talking about software engineers being able to develop in soft logic and FPGAs for a long time, but a big part of the reason it hasn't happened is because the tool chain is terrible, or has been terrible. And I think that that's going to change. I think that the indisputable end of Moore's law is going to accelerate that change as people have to get more creative. There is the end of Moore's law does not mean, by the way, that soft logic is going to save us, or that custom design is going to save us, or software hardware design is going to save us. It's going to mean that we are going to have to go to these techniques to deliver a more efficient system. So we are not going to continue to see the gains that we have seen, but we are going to be able to develop much more efficient systems by thinking of the hardware and software together. And I think that more and more people will blur that boundary between a hardware engineer and a software engineer. I think that's going to be in a very productive way. More people will care about this interface, or are going to have to. And I think that some of these real brute force techniques of the past, and a lot of this historical MLDL that relies on just massive amounts of data for somewhat middling results, I think we're going to begin to question that and begin to really look at this through the lens of efficiency as we look out 10 and 20 years.
So Alex, please wrap kind of your position for us.
Yeah, I think that essentially this comes down to the thing that, all of the arguments about the value of our co-debaters have said, it has really focused on, I think, kind of a desire to reverse this trend of abstraction away in a way that I don't think is productive. Ultimately, you know, the value of abstraction and the impact of machine learning and the impact of all of this is in the software, because it's in the experience that the users have at the end. And for me, you know, we can look at the power of abstraction in the way we see, going back to the car analogy, the ability to replace an internal combustion engine with an electric engine and then defer the problem of power generation to the scale out there. And you can only do that when you have abstractions. If I had to completely relearn how to drive an electric car, then we're going to run into the same problem day to day here. If we have tightly coupled hardware and software at the kind of team level or at the company level where everyone has to worry about these things, then we're never going to be able to conduct the sort of mean shift, the sort of substantive change in attitude across the industry that's going to be needed for us to do these things. I'm very happy for people to continue developing hardware. I'm very happy for people to think about these things, but I want it to happen in a room somewhere else. I don't want to have to have my own nuclear generator under my desk or I have to have my own solar panels everywhere, because frankly, those things don't scale as well as they do for me to rely on a grid. The ML grid is going to be there. I want to tend my data and I want to put that out that way. And I think ultimately all of the stuff about defining the power of open source has been about finding the type of abstraction that it turns out people can pick up and use and not worry about the internals of. And I think that to me is where the future of this is. And that's why it's about the software, not the hardware. And it's about the data and the people, not some sort of a reversion to a mean where I'm going to have to break out my soldering iron every time I want to do some text classification.
Awesome. And Anna, last but not least, please, bring it home for us.
Sure. Yeah. I think I wanted to respond to David's point about we shouldn't bet against software innovation. I guess my response is, why not both? And with the fate of the planet at stake, I think we have to do both. Hardware, software, co-design.
Well, awesome. So folks, like mentioned before, that was a kind of, a great way to I honestly, and again, not anything against the other panels that are going on, but it was just, so pleasant to see you all trying to, bite your lips before kind of responding in a while. So I think hopefully at least the speakers enjoyed it and the audience as well. I definitely enjoyed it. Thank you very much. And we ran the results. So apparently pre the debate, it was exactly 50-50 split. And after the debate, every single team convert every single person from the other team to their position. So it's a tie, and, job well done. And I think now, admins, do we need to go to another room for the Q&A session, or how does it work? So
before we leave, can we just say thank you to Vitaly for excellent moderating and supporting the debate?
100%.
Yeah, thank you.
Thank you, Vitaly.
Yeah, so I wish we had a little bit more kind of knowing. So is there a spatial chat that we need to be on? Or
is that the email they sent about? Hold on, let me see if I can drag that up.
So guys, if you, I think we can take a few questions here if there are questions for us in the Discord, and for more detailed Q&A, we can move to special chat. So I think maybe we can take a few questions here and then go there. And I actually have a question for you guys, right? So I kind of try to keep it. It's very hard to kind of keep this question, but so one of the things that I've seen right happening in this across our communities, right? And we're not talking about it. This is what I'm really interested about. So if you look at the rise of the clusters and AI, so GPU is kind of the elephant in the room. If you look at what's happening, right? So NVIDIA, the whole rise of NVIDIA, right, is basically due to GPU. And so it's what started as kind of a component of a PC, a gaming kind of apparatus, suddenly kind of broke through into the mainstream with many factors, right? So for instance, cryptocurrency and mining, right? And then AI and rendering. So what happened, and I wonder if if you might agree with this or not, but it is driving a lot of the economy, right? So NVIDIA became basically an economic powerhouse. It threatens Intel, right? So kind of the chip design, Apple is doing their chip design. So we have massive changes in the world economy because chips became a very important economic engine, right? And even now affecting the fate of the planet. And actually, for instance, I just recently learned that Adrian Cockcroft, who was a VP of open source at Amazon, now moved to actual unit of Amazon, which cares about energy savings. So his new job is essentially sustainability, meaning sustainability for AWS. So there are senior folks are moving into kind of leadership roles, caring about this stuff. But what really started this are these, chips, right? The becoming kind of at the heart. And so as software people, we're not really seeing that. We're on the receiving end. So how I've seen this happening, right? And I led a team which around the rise of deep learning. So how we experience this, like there are these GPUs. How do we go about them? There is CUDA. Now you need to install the CUDA library, right? It's not actually running everywhere. Like how do I install CUDA? I cannot install it on a regular Mac even. Like I need to have the GPU, NVIDIA GPU, and so forth. So to software people, this thing came through kind of pigeon mail, right? Like we got rumors about GPUs, right? We got some strange kind of ripples on the surface of the ocean, and so we kind of were extremely reactive, right? And so I wonder if you guys have opinions, because in my mind, it's actually driving enormous amount of change. But in the software community, we're not talking about it. And the hardware people are just pushing these things out the door. They care about like, let's have more kernels, let's have more, flops. So why is that we, it feels like we really in software community, we just have to like figure out, right? So on the one hand, to say it's the power of abstractions and we don't care is easy, but in effect, we do care. We're extremely powerless, actually. We are receiving so when I wondered, like when Bryan builds his data center and there is like this enormous API, is it going to change everything, for instance? So are we going to be kind of presented with the fact that now we have to do everything distributed systems differently? We have to relearn everything, and so that will actually, right? It's like if we think what matters the most, who is in the lead? Does it mean that hardware is actually in the lead or not? So I wonder if you guys can share an opinion on this.
I have a bunch of opinions here. Man, where to start? I think it's an interesting thing that if you ask Bill Daly, who is the CTO of NVIDIA, right, sort of what matters for ML, he would actually tell you it's not CUDA, right? It's TensorFlow and PyTorch on the training side, right? And so, the rise of the GPU is that, first of all, there was volume economics behind it, which was video gaming, right? Which is, accelerating approximations of light transport, which happened to resolve in vector processing, essentially. And then, my friend Bryan Cantrill sort of managed to connect that up to Python, to the machine learning world. And then Imagenet came along, right? And Imagenet showed that if you get enough data and you get enough compute, suddenly you can get these qualitative leaps in capability where, the computers are beating the humans, right? And, the GPU certainly was the vehicle for that. But, the days of like a lot of people, monkeying around in CUDA in order to do their ML are, to a certain extent gone, right? It is about TensorFlow and PyTorch. And like even at Google, I mean, I don't work at Google, but, right, the whole MapReduce paradigm is there to insulate people, right? Jeff Dean can't answer every query by himself. Memes to the contrary. And yeah, so, but I think the beauty is actually in connecting up the hardware with the software. I should be clear that I am actually a big hardware software co-design proponent myself.
I mean, I guess I would disagree. I think Jeff Dean can personally answer all the queries, but in terms of Anyway, in terms of, you were bringing up Imagenet. So like if we look at, say, a model like EfficientNet, which is one of those sort of state-of-the-art vision models,
Yeah.
like it just, the utilization on current hardware is just extremely poor. So like, I think we really can't ignore.
Out of curiosity, does anyone here actually know the particular like primitives that are in ImageNet that don't map well to, you know, like
That's why separable convolutions.
Ah, okay, yeah. That makes sense.
They're using up like, there's like 5% of the flops, and they're like 60-70% of the runtime on like VSTP.
Can I interject for a moment to explain the mismatch here?
Yeah.
So my understanding, and correct me if I'm wrong, is right, if you look fundamentally at something like a TPU, right, the power comes from having a very large matrix multiply array. It's about 128 by 128. A GPU is a bit smaller, but it's still, I think, 32 by 32, depending on the data type. And so the issue is with the depth-wise separable convolution, you're no longer actually doing a matrix multiply. You now have a very sparse matrix multiply rather than dense. And so, you know, really what's happening is, you know, most of what you're doing is multiplying 0, which is a very stupid thing to do because everyone knows the answer of multiplication by 0. Right. Exactly. And so, you know, we have this very fundamental mismatch. And I actually wholeheartedly agree that, you know, if you ask me the two biggest things that I think will drive ML performance in the next 5 years, it's advanced packaging and heterogeneous integration, and then being able to efficiently exploit sparsity.
And that's really correct. Especially the early layers have very few input-output channels. So they're using such a small percentage of the systolic array. And that's why.
Yeah, Brian, do you want to maybe answer the question that came up in the chat in a kind of broader form?
Yeah, so the question in the chat, which I thought was a very good one, was why is there no general purpose FPGA in our laptops that we can, why have we not seen, and I think there are a bunch of economic reasons for that, really. I think that part of the problem that we've had with FPGAs, again, is, I know it's very on brand for me to say it, but these tool chains are terrible. I mean, we were evaluating looking for a secure FPGA, which is basically a contradiction in terms. There's essentially one vendor who even attempts to make a secure FPGA. And we literally couldn't get their tool chain working at all. If it had been open source, we would have just fixed it. And the fact that it was proprietary, I mean, it's this flashback to how bad software was 30 years ago when you had to go deal with a vendor for everything. And that has been a real serious impediment. And that era, I do think, is ending, and we will see a real rise in reconfigurable computing and soft logic. And I think we will see, will we see it in a laptop? Hard to know, because as a development vehicle, there are a lot of economic constraints there as well. But I think we are going to see some of this promise deliver itself over the next 5 and 10 years as we get these fully open tool chains.
I have a question for you, actually. So what are your views on CGRAs, right? Because, you know, the difference between a CGRA and FPGA is the granularity of configuration, right? And I feel like, you know, that's one of the interesting things in the ML space is if you look at many of the accelerator startups, right, a large number of them are building what are known as coarse-grained reconfigurable architectures. So, you know, if you were to take sort of like the apex of this, it's like Cerebras Systems, which has an entire wafer with hundreds of thousands of cores with reconfigurable routing between them. And by reconfigurable, I mean sort of software reconfigurable, right? So it's not quite choose 7 bits or choose 16 bits, right? You give up, you know, one level of complexity, but, you know, you still have much of the power. I'd be very curious about your perspective on those.
Yeah, I think it's very interesting. Full disclosure, Cerebras and Oxide share an investor. So Eclipse Ventures has funded both. They're very much a sibling company. So just keep that in mind when I say they're a terrific company, and just know where that's coming from. But I think when the Cerebras approach is that disclosure made, the Cerebras approach is very interesting. And I think that what they've done is just incredible with wafer level silicon. I think what's interesting there too is if you look at why is AMD besting Intel right now in server compute, it's because AMD believed in chiplets when Intel was a chiplet disbeliever. It's kind of, it's nuts to me that one could not believe in chiplets, but they very much didn't. AMD very much did. And the rise of chiplets, to me, does allow you to change that dial of reconfiguration, where you're going to have a chiplet, and now that chiplet is going to have a fixed function, and now you're going to lay that down onto a larger package, and the kind of the flexibility that affords you. Now, I think that the flip side of all of that, again, to be back on brand, is that you end up with these very complicated machines on the die. The die itself now looks like a data center, and it's really problematic when that's all proprietary. Right now, there's an excellent Timothy Roscoe keynote at OSDI this past year. Really recommend that folks watch that, where he talks about something that those of us in the industry know, which is that these CPUs have become ridiculously complicated with many, many cores that are not the cores that you see, many, many hidden cores. And I think part of delivering on the ultimate promise of that is allowing other folks to reconfigure that differently, to get transparency into the decisions that have been made there and the software that is running on those many cores. I mean, long answer to the question, David, but I think that I think there's a lot of promise there, and I think the ambiguity in what we consider to be reconfigurable computing from a gate level through a hard logic level, a core level, I think that ambiguity is healthy and important, and it's going to be really interesting.
Yeah, well, again, I would like to thank everyone for being here for, I think what Alexei, it was like the longest session ever in Scale by Debate. It was in fact so long that Facebook no longer exists. So during the session, Facebook is now changed its name to meta.com. So anyone who's interested in checking it out or has any final statements about the rebranding, but other than that, again, it was a joy, pleasure. Alexei, thanks you for inviting us to this conference.
Yeah, this was fantastic. I want to thank all of my co-panelists and our moderators and instigators. This was actually really fun.
It was a lot of fun. No, absolutely accurate. Thank you very much.
Bye.
Thanks,
Bryan,
folks.
we should talk Intel's 10 nanometer over a drink where there's no microphones.
Thank you, guys. Yeah, and I must say that David and I, we kind of, we're chatting on email. We anticipated actually one of these name changes because I actually mentioned the company behind the Dumbarton Bridge. I didn't actually know about anything which is going on, and then I realized that's what's happening. So thank you again, guys. This is amazing. So now, if folks who can check out our special chat, there is a button for Q&A. So if you guys some of you want to go there, we can go to special chat. So you should have received the link to there. For viewers, there is a button called Q&A, and so that actually goes into the special chat environment, and definitely go there and see if there are any folks there who want to ask us questions. But that ends the official part of the panel. Thank you very much, guys, and we'll see you in special chat.